Welcome to the first part of tutorial chapter 11. In this chapter, we will learn about monster and mixture, which are two types of advanced models to help us solve some common issues in standard models. Of course, these models are harder to estimate and to understand, but they are also important tools. The good news is that Stan provides us a quick way to simulate fake data and then recovering the data generating process by fitting the model and to help us learn these kind of complicated models easily. One of the most common issue in the counting model, like a binomial model or Poisson model, will be over-dispersion. So what does over-dispersion mean? So in binomial model or Poisson model, the variance is a function of the expected value. So for example, the expected value and the expected variance of a Poisson model will be the same, lambda. And for a binomial model, the expected value, or we can call it the mu, will be n times p. However, the variance will be n times p times 1 minus p. So what's the problem? Basically, this kind of situation will decrease the degree of freedom for binomial model and Poisson model. Because once we know the expected value, variance is determined. But in the real world, the data we usually observe has a larger variance than the expected result. When we were in these kind of situations, just using the simple binomial model or Poisson model will not be a good idea. So in this part, we will learn the two more powerful versions of binomial model and Poisson model, which is beta binomial model and gamma Poisson model. So let's start from beta binomial model. In this case, we will use the UC Berkeley admit dataset, for example, again. And now, if we don't have the information department the applicants applies to, how can we still make the correct inference that gender effect is not significant? Let's recall what we did in previous chapter. In chapter 10, when we only consider gender effect, we use a very simple model where we have two alpha values to estimate two p values for male applicants and female applicants. And the likelihood function we use is a very simple binomial likelihood function. And the result is that there is a big difference between the admit rate of male applicants and female applicants. However, that was a wrong interpretation because after taking departmental information into consideration, we will see that gender effect here is actually not a big deal. If we transform this logic value to the probability scale, you will see that it's only about 2% difference in male and female. So what can we do if we just don't have the information about which department they apply to? So let's start from first principle. A very straightforward solution for this problem is to assign different probabilities to different rows of the data. Like we know that maybe they're applying to different departments, but we don't know like which department they apply to. But we can like assign different we can estimate admit rate row by row. Estimating the probability row by rows is actually the intuition of the beta binomial model. But instead of assigning these probabilities individually or manually, we can use a beta distribution to describe the distribution of these probabilities. If most of you are unfamiliar with beta distribution is used to describe the distribution of any proportion or probability values. Defined range of beta distribution is from 0 to 1. There are two parameters in beta distribution, like the mu and standard deviation in a normal distribution. So p bar suggests the average probability, and theta will describe the deviation of these possible p values. So if we set p bar equal to 0.5 and theta equal to 2, and the accruing beta distribution is like this, we expect the proportions from 0 to 1 is around uniformly distributed, except on the two tail when p equal to 0 and p equal to 1. And if we set theta equal to 1, so it says a different story. Now we expect it's more possible to have p on the two tails, but not in p equal to 0.5. And if we set theta equal to like 10, we expect the possible p-values be concentrated at p equal to 0.5. So what's the advantage of using a beta distribution instead of a simple binomial distribution? If we use a simple binomial likelihood model, it's like only estimated one point in the beta distribution. But if we use a beta distribution, well, it will be a distribution of proportions. So each row of the data can represent one point in the distribution, but we can collect all the information from each row to form one beta distribution and to see what is the p bar and what is the theta of this beta distribution. And we can use the p bar in that beta distribution to represent our data. With the basic understanding of the beta distribution, we can start to build our STEM model using a beta binomial likelihood function. So what are the required modifications? Let's begin from the old model we use. So the old model, we first use the logic transformation to match the p to the whole real number lines, and then use the binomial likelihood function to estimate the p value here. And actually, in beta binomial model, it's pretty similar. So we use the logic model, logic transformation to transform p bar to the whole real line. But we change the binomial likelihood function here to a beta binomial likelihood function and then add a theta. So coding the STEM model is very similar to what we did in chapter 10. So the data, the parameters, the transform parameters part are all the same, except that we need a new parameter theta, and don't forget to set a lower value equal to 0. And in the model part, you will think that it's a little bit different why the beta binomial model is more complicated than what we did in the previous line of code. So the reason is that the standard default beta binomial model has different parameters than we did. So I provide some comments here. So this is the default parameter in the stand function. So the two parameters are shape 1 and shape 2. But how can we transform shape 1 and shape 2 from probability p bar and theta? So shape 1 is just p bar times theta, and shape 2 is just 1 minus p bar times theta. So you can see that actually here is p bar times theta and 1 minus p bar times theta. It's very common for some advanced or distribution functions that we have more than one kind of parameters to describe the same likelihood function. You just need to get used to it and find the documentations to make sure what kind of parameters are used in this language. In the generated quantities block, nothing new except that I add a new parameters called differences in p bar to record the difference in male admit rate and female admit rate, so we can directly compare the results from stand output. And let's see the result here. So you can see that p bar 1 and p bar for male and p bar for female are very similar, and the difference in p bar, the mean value is very close to 0. And if we look at the distribution of the differences in p bar, you can see that it actually crossed 0, so it's not significant. So we arrive at the correct inference that gender effect is not influential in the UC Berkeley admit data, and we didn't include the department information. Surprise? Yes, this is the power of a monster model. A posterior means we also want to plot the whole distribution of the beta binomial model and the predicted admit rate. Begin by plotting the posterior beta distribution of female and male admission rate. The stand output, as here, will be 2000 combinations of p bar for male, p bar for female, and theta. So these 2000 rows of data represent 2000 kind of different beta distributions. We would like to plot each of them. Plotting a distribution using the parameters is something new for us. In previous chapters, if we want to plot a line, usually we will have the values on a lot of x and y combinations, and the line we draw is like connecting these dots of different xy combinations. But now we don't have these xy combinations. We only have the parameter for the beta distribution. In base R, we can use the curve function to do this. And in ggplot, the alternative function is called a stat function. The trick to use the stat function method is that we need to make a customized d beta function which has default value for p bar and theta 2. Because the original function we use, this d beta 2 function, has no default value for p bar and theta. So the stat function cannot recognize this d beta 2 function. So here I create a custom d beta function and just assign the default value like p bar equal to 0 and theta equal to 2 to the d beta 2 function. And then I use a for loop here to iterate through the parameters output by the stand function and assign them to the customized d beta function by the args parameter in a list. Some of you may notice that I only sample 200 rows from the total output I have. That's because plotting 2000 lines will be very time consuming and requires a lot of computation powers. Plotting 200 of them will be representative enough. Besides plotting the samples we have, posterior outcomes, here I also plot the posterior mean of male and female data. Use the blue, assign them to be blue so we can separate them from the samples we have, and the result will be like this. So you can see that the posterior mean are very similar for male and female admission rate, and the posterior samples are not that different as well. Second plot we want to have is the posterior prediction admission rate for different cases in the data set. The blue dots are the actual admission rate for different cases, and the blank and the open circles are the posterior mean prediction, and the lines are the confidence interval, and these are the prediction interval values. There is nothing new tricks we need to have a plot like this, but predictions for all male applicants and all female applicants. So you will see that for 1, 3, 5, 7, 9, 11, like the predictions are the same, and for even numbers, the predictions are the same. So how can we achieve this? The trick is to use an if-else statement. So you can see when prediction mean and confidence interval include the if-else statement. That's because the data we have is just the p-bar value. So it's one value, it's not 12 values. So we have to assign them using the if-else statement. So if the case is an even number, we assign the p-bar of female admission rate. And if it's not even numbers, we assign a p-bar of male admit rate to it. But for prediction intervals, we don't need the if-else statement. That's because in our posterior result, we have one parameter's prediction count, and the prediction count has a parameter has 12 values from case 1 to case 12. So the result is like this, and we can just need to calculate the mean of each predictions, and just need to calculate the prediction intervals for each of these 12 values, and as the prediction intervals upper bound and lower bound. So with all these data, we just need to plot them using geometric points, geometric segments, as we did in chapter 10. And the result will be like this. Okay, we finished the beta binomial model, and we are ready to jump to the gamma Poisson model. So the gamma Poisson model is very similar to the beta binomial model. The difference is that it uses a gamma distribution to describe the lambda of the Poisson distribution. We will use the ocean tool example again, and let's review what we did in chapter 10 first. This is the posterior plot from the final model in chapter 10. We can tell that the low contact rate islands are highly influenced by this point. This is Hawaii. Because of Hawaii, the variance for low contact rate islands in larger populations as predictions are much smaller than that for high contact rate islands. The variance for larger population islands of low contact rate should not be that low. We can see that the prediction mean just crossed the Hawaii island. So it's actually an overfitting problem. How can we avoid this problem if we were not given any new information? The gamma Poisson model is here for help. It can solve this problem by adding more variance around the expected rates for low contact rate islands to avoid overfitting. This kind of modification is also simple. We just need to change the likelihood function we use in the model block from Poisson to negative binomial 2. Why use negative binomial? Actually, this is the other name of the gamma Poisson model. If you look at some papers, sometimes maybe you will see a model or a distribution called NBD, and this is the negative binomial distribution or negative binomial model. The 2 here is because there are more than one way to parameterize a negative binomial model. So STEM provides us like negative binomial and negative binomial 2. It just depends on what kind of parameterizations we want to use. And in this case, we want to use the parameterizations of lambda and y. Let's jump to the STEM code of the gamma Poisson model, and you can see that I modified the model likelihood code here to negative binomial 2 and add a new parameters called y as a real in the parameters block. It's done. Nothing changed, actually. Posterior result is totally different. We can use exactly the same code from chapter 10 and to plot the posterior outputs of this new model. And then, surprisingly, wow, the gamma Poisson model actually truly add lots of variance to the low contact rate islands. And now the prediction means do not cross the Hawaii island. So we are confident that the overfitting problem is somehow avoided. Using these kind of monster models like a beta binomial model or gamma Poisson model is one way to solve the overdispersion problem, but this is not the only way. In chapter 13, we will learn about another way, a more flexible method called a multi-level model. With multi-level model, we can assign our own prior distribution on the prior of the model. So the higher level prior is called hyperpriors, and we can just comparing the parameters of hyperpriors of different genders, we will have similar results from a beta binomial model. We will learn about the details in the future, so no worries about that. Just want to let you know the monster model is not the only way. Okay, let's move on to the second part of this chapter, mixture models. So why we need mixture models? In many occasions, the data we observed are not emissions from any simple process. Instead, they can be a mixture of multiple processes, like it can be firstly a binomial process and Poisson process, or a binomial process and then a normal process, something like this. So a mixture model is a kind of model that we use more than one probability distribution in the model to simulate or to fit the data. The data we use in the mixture model is simulated or fake data. So, but let me explain the simulation process first. So imagine there is a large number of monks like copying a small number of manuscripts every day, and this copying process is a Poisson process. But just like us, monks drink on some days. On those days, no manuscripts are completed. So this is a mixture process. There will be zeros on working days and drinking days. If we want to estimate the correct lambda of or the correct mean of their speed of copying manuscript, we have to estimate how often they drink at the same time. Modeling a problem like this will be a little bit complicated if we just use the traditional machine learning techniques. But with the help of Stan, it can be solved easily. All we need to do is to translate this description into a math formula. So the result will be like this. When we observe the outcome, the completed manuscript is zero. It can either be that the monks are drinking that day, or they are not drinking, but they just can't complete any manuscript on that day. When we observe at least one manuscript, monk must not drink that day, and the monk must complete at least one manuscript that day. These two formulas are just the mathematical version of the story I just tell you. The next step for us is to make Stan also understand our math story, and Stan also only understand the log likelihood version of the statement. So we just need to take the log on both of these two formulas. So you can see here, I take the log on the first line, and I replace p drink with just p, and replace the PR 0 given lambda with a more detailed version, like I put a Poisson distribution here, make it clearer. And for the second line of the formula, after taking the log, the multiplication now becomes plus probability of Poisson y larger than 0 given lambda. After taking the log, it becomes a Poisson LPMF. So it's a little bit different here because we have the log on the probability, it becomes LPMF. But here in this line of code, log is still here, so it's still in the probability form, not the LPMF form. Next, we need to code this model using Stan syntax, and there are some tricks modeling this kind of mixture model. We will use the logmix function to calculate this complicated log likelihood. From the Stan guidebook, we can find that the logmix function is defined like this. So there are three parameters in the logmix function: theta, lambda 1, and lambda 2. So the logmix function will calculate the log value of theta times exponential lambda 1 plus 1 minus theta times exponential lambda 2, which is very similar to the complicated formula here. So let me show you how can we start from the complicated log likelihood function we have to the log mix version. So let's take a look at this function. P plus 1 minus P times probability Poisson 0 given lambda, and can be denoted as P times exponential 0. This is actually 1, right? And plus 1 minus P times exponential Poisson LPMF. So this is the probability version, but we want to have an exponential statement here. So what can we do? It's very simple because exponential and log is the inverse calculation. If we take exponential on the log version of the Poisson function, and it will be the row probability function. These two lines are the same. And then we arrived at the log mix parameters. So exponential 0 is the first lambda, and the theta is p, and Poisson LPMF 0 given lambda is the lambda 2 parameter of the log mix function. Don't worry about that if you don't understand this transformation at your first glance, because it takes me like 2 or 3 days to understand how this function works. You can just check the reference here for more detailed information. The second line of the math formula is easier, but for the log 1 minus p function here, use the log 1 minus function instead of just using log 1 minus x directly. Because log 1 minus function will ensure that there's no precision problem when 1 minus x is very close to 0. Tricks, we are ready to build our own STEM model. Let's begin by simulating some fake data. So firstly, we can set the probability of monk being drinking is like 20% of days, and the average manual script they can copy is like 1 page a day, and we have like 365 days in a year, so we can make a data frame like this. So firstly, we use random binomial function to determine if the monk is drinking that day. So it's the first column in the data frame. So if it's 0, the monk is not drinking. If it's 1, the monk is drinking. And then the second column is the output. If the monk is drinking, drink will be 1. So 1 minus 1 will be 0. The output must be 0. Means that if the monk is drinking, the output must be 0. And if the monk is not drinking, drink will be 0. And the output will be determined by random Poisson with the average rate of work being 1. The result will be like this. The monk is not drinking, but output is 0. The monk is not drinking, output is 2, and the monk is drinking, output being 0, monk not drinking, output also be 0. And we can visualize the result like this. The gray bars are the result, the output from Poisson, and this blue bar is the result from monk being drinking. So you can see that we have much more output being 0 compared with a usual Poisson process. If we ignore the fact that the 0 output is not only from a Poisson model, but also from a binomial process, the estimation of the parameters of this data will be highly biased. And then here we just apply the tricks we learned, the log mix function and the log 1 minus function into our STEM model. So the data, the parameters, the transform parameters are we are very familiar with them. Just be careful that p should be transformed using the inverse logic function because the value of p is from 0 to 1, and lambda should be transformed using the log function or exponential function because the value of lambda is the whole positive real numbers. The new things are in the model part. So here we have our log mix function and the log 1 minus function. But you may be wondering what is this target plus equals means. So let's look at the STEM guidebook again. The sampling statement we are familiar with is like this. Y tilde normal mu and sigma means that the output Y should follow a normal distribution of mu and sigma. But this is actually a short version of this target plus equal normal LPDF. So what is this target? So target is actually an implicit variable inside STEM, and target will record all the likelihood functions you want to optimize. Our case, of course, we don't have the short version of this like normal function STEM, so we have to use target plus equal the likelihood function, our customized likelihood function, like here. So we use some if-else statement. If y is equal to 0, likelihood function is this log mix function, and if y is larger than 0, the likelihood function is log 1 minus p plus Poisson LPMF. Let's build the model and see what the output is. You can see that Sen is successfully estimate the correct parameter values. The probability of monk going to drink is 0.2 and the lambda is 1. Understand how to deal with this kind of zero inflected problem. And this is the end of the first part of tutorial chapter 11. Don't forget to watch the second part of chapter 11. See you next time.